Okay, so that is about a brief introduction about the teacher. Next is about the subject. We'll start about the subject. So control systems. What is control systems? So its definition says it can be a device. Basically, it is a system, and it can be a device, or it can be an algorithm, or it can be even a set of devices. So what does these do is it manages the commands, or it manages and commands, then regulates the behavior of other devices or system. Okay, so the basic definition goes like this. Example is a brain. The best example is a brain, or a heart, or CPU of your computer. So we can say that brain is a device. Just for the sake of simple understanding, let us call brain as a device. So what does our brain do? It will manage, command, direct, or regulate everything in our body. So we call it as a control system. A brain is a control system of our body. Okay. Then our heart. So it basically regulates the blood pressure in our body. Okay. Of course, indirectly it is again controlled by brain. So we can call heart as a subsystem. As a subsystem which controls our blood pressure. So it is one of the example for control system. Then CPU, the central processing unit, of course, it manages everything that we operate in a computer. So it will basically have a microprocessor in which some architecture is designed to do the operations. Fine. So these are simple definition. I hope everyone can understand. Let us not make any complications about this. Next, what is a system? Okay, we know control system now. In that, let us pick a word system. What is a base system? How we can define a system? Any physical structure that responds to any given physical input can be termed as a system. So in simple definitions, I can say my pen is a system. Okay, or a stone, or a door, or a fan is a system. So when we say stone as a system, and when you apply force on the stone, obviously it will respond by getting displaced. So the output or the response of the system is in terms of displacement. So it is responding to a physical input. Okay. So that is simple system. Next, the complex systems are aeroplane, computer, car. Okay, just hold on. There are some queries. Anybody is not able to hear, somebody is chatting a message in the chat box. So let me attend it because this is the first class. Let us try to tackle all the problems today itself. Okay. Sir, please speak louder. Fine. Okay, I'll take that into okay. Please speak louder. Fine. Okay, so we'll continue that. The complex systems are aeroplane, computer, or car. So why these are termed as complex is apart from one single system, there exist different subsystems also. Okay, that needs to be managed or controlled. So we call them as a complex system. So we can expect at least second to third level of subsystems in a complex system. Then the third category comes as a highly complex system or high complexity systems. So that is a missile or a satellite or an autonomous robot. So why these missile or satellites are called as high complexity systems is because the control task is not so easy. Even a brain can be termed as highly complex system because we ourselves don't know how much work it does, what sort of control actions it creates, does to maintain our body in a stable, maintain our body in stable. So there are so many parameters need to be considered while controlling a complex system. So I could say only a doctor knows the capacity of our brain to a deeper level. only a scientist knows how difficult it is to control a satellite or missile. So we'll come to that part while we study some of the applications or case studies in future chapters. So going to the next part. So what are the prerequisites for this subject? So physics can be represented in mathematics. If you know this much, that is more than enough. Okay, that is sufficient. So we should know the physics of the systems and how to represent that in mathematics. So before proceeding with some more mathematics or in deeper, so I would like to ask few questions to you. So we have already studied or you are aware of Fourier transform or Fourier series. Fine. So how many of you know the practical meaning of a Fourier transform or series? So that matters a lot. Why we use Fourier transform or series and how we use them. So that understanding is required. Okay. So this kind of a study or the study in this orientation is very much important. It's not just solving a numerical of set of equations and producing the answer. You should be aware of the practical importance of the transforms. Then similarly, you might have already studied the Laplace also. So what is the practical meaning of Laplace transform? Or why we need the Laplace transform? What is the difference between Fourier and Laplace? And how differently they are applied? Okay. Then where the Laplace or Fourier fails? Is there any failure that we cannot apply to certain signals or certain signals? So this kind of understanding is very much essential for control system. Okay, so one thing I would like to clarify here, there is no unique way to control anything. Okay, unique way in the sense there is no unique algorithm or unique device you have to develop. You can develop an algorithm or a device in many ways considering many parameters. So that's why we should have a thorough understanding of Fourier and Laplace. So of course, since this is an online class, I cannot give an option to answer the questions, but try to question yourself and try to find these answers. And once the group is created, you can post your queries or questions anytime. I will try to answer everything, provided you come with some answer, whether right or wrong. Okay. Then the practical interpretation of mathematics is very important. Okay. So this of course is quite complex when we compare with engineering mathematics. Okay. So practical interpretation is very much essential. Every time whenever you write an equation, please remember you should always try to practically interpret its meaning with some sort of benchmark examples. Okay. Then the last prerequisite or the much important prerequisite is imagination. Imagination of practical and ideal environments. What you study in the books is most of the time with respect to ideal environments. When we go to practical environments, the challenges will increase. Then how to tackle such a practical scenario is very much essential. Okay. So considering, say, for example, if you have a, if you are designing some spring for a door system, then when you do a mathematical calculation, the answer you will end up, say, suppose the spring constant should be, say, X for this door for a proper operation. Okay. I mean, you do some mathematical calculation by hand and you will give the answer that, okay, the spring constant for this, so this door must be, say, X. But when you design a spring with the same spring constant and use it in practical scenario, your system may behave differently. Okay. So your system may behave differently because in calculation you might have ignored the friction at hinges. Okay, so such sort of practical environments will come into picture. So a better imagination will always give us a better design of a control system. So that's what the important requirement is. Okay, then where you can apply the application of control system. So these are the some domains of applications. You can apply it in aerospace, and the major domain in aerospace is flight dynamics and control. In mechanical engineering, it's automobile applications, for example, autonomous cars or self-driving cars. So for that, we can use control system. Then in civil engineering, the control system is applicable for structural design for earthquake resistant buildings. Then control system is applicable in biotechnology. So artificial intelligence. Okay, nowadays the application of control system in biotech is huge. So it is mainly called as a bio-inspired control techniques. Okay, these neural networks, deep learning, machine learning are a kind of bio-inspired control techniques. Next, it is applicable in chemical engineering, chemical industry, such as process and pharmaceutical industry. Then, of course, it is applicable in electrical engineering, like machine control, basically the speed and torque control of a machine. Then it is applicable hugely in power systems and power electronics. Okay, so to briefly discuss about applications in electrical engineering, let us consider a machine control aspect. So basically, we can take a robotic joint and imagine, just for the sake of simplicity, I'm telling that in the robotics, imagine you are using DC motor at a particular joint. Okay, of course, it is not always DC motor, but just for the sake of simplicity, imagine we have used a DC motor at a certain joint. So the movement of, suppose, say, arm, which is connected to joint, is controlled, of course, by the motor. Okay, so motor, there are two aspects of motor control. One is speed control, another one is a position control. So basically, when we use it for robots, it is more about position control of the arm. If you want to rotate your arm by, say, 10 degrees to 20 degrees, or 0 degrees to 20 degrees, okay, or 30 degrees to 45 degrees. So for that sort of application, you need a precise control signal. You need a very precise control signal, because you cannot take a chance by creating an error of 1 to 2 degrees. It will cost you a huge means huge. So that comes under a machine control aspect. Then power system is a very challenging area in control system domain. So what needs to be controlled in power system is that, suppose, say, you are taking power from generating station to the distribution and finally to the end users, customers. So there is always a chance that the variation in power demand is non-linear. Okay, is a non-linear. So what happens, the exact way to divert this power demands is very much essential in terms of control controllability. Okay, so this is a very huge research domain also, as it is a non-linear system. Power system is always classified as a highly non-linear system. I hope you are aware of linear and non-linear system. Okay, so if not, just revise what is linear and non-linear meaning. And then comes the power electronics. So the control application in power electronics is mainly in terms of charging and discharging of batteries. Okay, then generating pulse width modulated signals to operate rectifiers, okay, or inverters. So you need to have a definite control algorithm to operate uh, charging circuits or driver circuits. So these charging or driver circuits are basically made of power electronic devices. So that is one of the major application of control systems in power electronics. And the last one is medical instrumentation. So controlled injection of drugs is one of the research area. Then robotic control surgery. So robotic control surgery, I was giving one of the example of machine control. So you can imagine, if you use a robotic arm for a surgery, how much important the accuracy is. Okay, even a 1 degree is a too huge error when you consider it for medical instrumentation. So that's why the control system is like, it is not limited to electrical engineering. So as per my knowledge, it's basically like, if you know any system and if you want to control, you can use your control system knowledge. So I'll clarify it once again. It is multidisciplinary domain. The subject is multidisciplinary. You can apply it anywhere with the knowledge of a system. So what control system basically needs is the mathematics and coding and understanding of physical system in the domain which you are working. So if you are working in flight dynamics, you should know the dynamics of flight completely. If you are working in civil engineering, you should know the structures thoroughly. Okay. So in that way, you can apply it anywhere. The knowledge is multidisciplinary. So some of the well-known experts in the domain of control system. So these are referred as the best researchers who have contributed very much for the subject. Okay, in 1960s or 1930s during World War and all. So the major research took place during World War, and the person here is Thomas Kailath. He's an electrical engineer. Okay, and his book is referred as Bible of Control Systems. Bible of Control Systems. What I felt after reading his book is like for every sentence, we need to understand a lot. For every sentence in his book, we need to understand or search a lot. So it's a very, very toughest book, a very toughest book. But if you complete studying this book, it means it will teach you mathematics, it will teach you signals and system, it will teach you physics, everything. So some of the questions I had asked earlier about Fourier or Laplace, you can find the answers in his book. Though it is difficult to understand, but he has given some hint about it. Next one is Rudolf Kaman. This Thomas Kailath is an Indian scientist actually. He's from India. Next one is Rudolf Kaman. So he is also very well known in that domain. Many of you might have heard about Kalman filter. Kalman filter, if you have tried to work on drones or quadcopters, you might have heard about Kalman. So again, he is one of the major contributor for the subject. His domain is basically in the field of guidance, navigation, and control. So more about satellites and missiles. Then there is another person, and I shortly spell it as K. Ogata. He is one of the Russian scientists. He has written a very uh, good textbook on control system, very basic textbook on the control system about fundamentals of system modeling and all. Okay, this is one of the reference book. This author has given control system engineering, and it is one of the reference book for your syllabus. And other scientists or researchers are Benjamin Koo. This is also one of the reference book, and the title is again Control System Engineering. Norman Nice is another author. His book is also very nice. Its title is Control System Engineering. And there is another scientist, William Wolowich. He has written Advanced Control System Engineering textbook. It is a bit complicated. If you are interested in higher studies, you can refer this.